Alright, so what we're talking about in this final video is an example of work and energy and really all this kinds of stuff is just going to fall together. Suppose I have, let's say, a metal plate, and on this side we have negative charges. So let's say I've got negatively charged conducting metal plate on this side, which means that there's a lack of protons here. So we got an excess of electrons on this particular metal plate. You're going to learn all about this stuff soon. And on this side we have positive charges. All right, so this metal plate here is positively charged. Now, in electricity and magnetism, I'm going to teach you all about charges and how there are two kinds, positive charges and negative charges, but I kind of think you got a hunch from that already since you've had some chemistry and you know that like charges like charges repel, opposite charges attract one another, and so that's the game. So you have this plate here negatively charged and this plate here on the right positively charged. These two plates will experience a force that'll tend to want to pull them together because they're oppositely charged. But let's assume that we're on a table and these two guys are locked down so they can't move. All right, they're not moving anywhere. And what I'm going to show you is, let's say I have at this position right here a very, very tiny electron. And I'm going to show a little minus charge right in there. So there's an electron sitting right at the surface of this positively charged plate. And just to be funny, let's say I've got my finger on this electron right here and I'm holding it. Right? The electron doesn't like to be on the negative plate because remember, like charges want to repel. So this electron doesn't like sitting there. It likes to go to the positive charge, and it's going to experience a force if I release my finger. Of course, you can't hold an electron with your finger, but just for the sake of this little demonstration or example that I'm trying to stress some concept, let's say we take this electron here, and at time t equals 0, the electron is here and it's at rest. So it starts at rest. Time t equals 0, I release the electron and it begins to move. So it goes from an initial velocity of 0 to some velocity as it now proceeds to move towards the positively charged plate. So it goes through the air until it winds up right there. Now, the reason that the electron is going to move and change its velocity from rest to some, over here it's traveling at some final velocity when it finally strikes the plate, right? The reason that's going to happen is that something's going to push it. So what is it that's pushing or pulling the electron from the left side here where all the charges are negative to the right side where all the charges are positive? That's something that's pushing this electron is what we call the electric force. So there's a force, an electric force that's going to push this electron in this direction. And get it to move. And that electric force is going to have to then do some work on the electron because the electron's going to experience this force in between the plates that's going to say, hey, here you're a negative, here you're a positive. You got to move over to the positive side because we're attracted together. So it's going to pull it. That pull is coming from a force. That force is the electric force. And so since the force is acting and the electron is having a displacement, right? It's at some initial position here, and now it's at some final position, which means that there's a displacement in this direction. Notice there's a force in this direction and a displacement in this direction. So the work done by the electric force is going to be the magnitude of the electric force times the displacement, which in this case is the distance, d, that it travels between the plates. And you could calculate that. If you know what that force is, you know the distance between the plates, you can find the work done by the force. But the work done by the force is going to do something to the kinetic energy of the electron. It's going to change it, because the net work done on an object, we said last time, I'm just going to switch back to white, is equal to the object's change in the kinetic energy. So its change in kinetic energy is the final kinetic energy minus the initial kinetic energy. By the way, anytime you see this delta symbol, it's always final minus initial. Ingrain that into your memory for life. Final minus initial equals change. All right? So the final kinetic energy minus the initial kinetic energy. So it's got some 1/2 mv final squared minus some 1/2 mv initial squared, but it was at rest when we released it. So this guy was 0. So you see, you can now calculate certain things that otherwise would be pretty difficult. You can actually find, if you know the mass of this electron, you can find its final velocity simply knowing what the electric force is and the distance of the separation between the two plates. And we're going to show you in the course how to calculate and find that electric force. The main point here is that when we talk about work, we're talking about force being applied to something to move it. Okay? Forces that are perpendicular to the displacement never do any work. Only the parallel component does work, and that's why it's technically a dot product. In this case, the force is in the same direction and parallel to the displacement. Here's the displacement vector. Notice here's the force vector. They are parallel to each other in the same direction, so we can simply take force times distance, because the cosine of this angle, what's the angle between these two? 0 degrees, right? And the cosine of 0 degrees is 1. So that cosine of theta, that just became 1. So the work done by the electric force on the object resulted in the object changing its kinetic energy. And I think that's about it for right now.